And yet one more example to kind of sort through all the pieces. But notice in this one, they don't come out and tell you to compute this or to compute that. You have to know what they're asking for because you understand what the different things produce. Let's see. So kind of a metaphorical thing here as well. I keep saying metaphor, but it's what we got here. You're standing at a point 113 on a hill whose equation is given by. So this 5y minus x squared minus y squared is kind of like a mound. You know, you think of a hill, and you're at the point 113. You could go any direction you want, but you choose to climb in the direction of steepest ascent. Now, when you read those words, in the direction of steepest ascent, your brain should now go, gradient vector! I hope it does. So we're going to take the gradient vector. Let's just go ahead and call this, as we like to do. This is a function of x and y is z, and this function is, I guess we could assume by this context that this is like an elevation. And so this is an elevation. Do we have any units here? We do not. So these are just elevation units. And so what we're going to find here is the gradient vector of f at the point 113. And to do that, to get this vector, we take the partial derivative with respect to xi, partial derivative with respect to yj. Notice my notation here. It's a vector. If you're doing a gradient, make sure you have a vector. If you're doing a directional derivative, make sure you have a scalar. If you're doing a magnitude of a vector, make sure you have a scalar. But the gradient is a vector, and it's in the direction of that vector that you're going to have the greatest ascent, in this case, the steepest ascent. And so let's do it. Come over here and get my partial derivatives. Pretty straightforward. The partial derivative with respect to x. So constant, it's just going to be negative 2x. And we want to evaluate this at the point 1, 1. And so negative 2 times 1 is just negative 2. Partial derivative with respect to y. So only this term is constant. So the derivative of 5y with respect to y is 5. The derivative of minus y squared minus 2y. Evaluated at the point 1, 1. So 5 minus 2 times 1 is going to be 3. So the gradient vector is going to be negative 2i plus 3j. So if you're at the point 113, now I'm going to do at least the two-dimensional version of this. So we're at the point 1, 1, and we're 3 units out. I know you can't see that, but we're 3 units high above that point 1, 1. Let's say it's right here. Now you can move in any direction you want, but if you go in the direction of negative 2i, from my perspective, I don't know if I'm mirroring this or not, but negative 2i plus 3j. Let me do it on here. If you go negative 2i plus 3j, not to scale, but if you kind of head that a direction, you're going to see the greatest increase. Now, it asks, what is your initial rate of ascent? It doesn't say, just stop there. It says, what is the initial rate of ascent? So if you're at the point 113 and you're spinning around, but now you finally know you're going to go that way. You're going to go negative 2i plus 3j, and you're going to take that initial step. Your increase in elevation will be what? Well, magnitude. Negative 2 squared, 3 squared, 9 plus 4, square root of 13. Now I'm looking at over here. Oh, they didn't simplify it. I was going to look to see if we have a simplification, but this would be, we don't have any units. So this would be, if you step in that direction, your elevation would increase by, can I make it, let's say these are in meters. Your elevation would increase by the square root of 13 meters for every meter in the direction of, here it comes, that gradient vector. So you're at 113, you're standing on a hill, you're going to go that way. You're going to follow the vector negative 2i plus 3j. You take a step. Metaphorically speaking, that step is going to be the square root of 13 meters tall. And at that point, 113. Now, it's all going to change as soon as you get off 113, unless you have some kind of a constant rate of change. But if not, we don't in this case. If not, it's not all going to change. But at the point 113, that initial rate of ascent, square root of 13 meters ascent for every meter walked, which is why they're saying relative to the horizontal distance. So for you walking kind of horizontally, your elevation is going to increase the square root of 13 meters. Now, what if you decide to go straight northwest? Now, we're still at the point 1, 1, and we're going to go straight northwest. So north, south, east, west, right? Now, straight northwest, when they say that, means relative to the horizontal, you've got a 45-degree angle. Now, if you've got a 45-degree angle, then there's some geometry here that I don't want to really spend a ton of time on, but there's some geometry here that would say this. A 45-degree angle would be that this leg and this leg are the same. The tangent of 45 degrees is 1, and so I know that this and this are the same. Let's just make them 1 and 1. So if I go 1 this way, so in other words, if you go straight northwest, the vector that we're speaking of, at least is in the direction of the vector, negative 1i plus 1j. I hope you see why I say that. We're northwest, so negative 1i plus 1j. Now, I do not believe that that is a unit vector. I'll prove it to you. The square root of negative 1 squared plus 1 squared. Yeah, look at that. It's the square root of 2. And so to make this a unit vector, we'd have to divide by that magnitude. So we're going to go in the direction of vector u. All right, if you do, will you be ascending or descending? At what rate? Now notice we are no longer following a gradient vector. We're not talking about steepest ascent anymore. We're just going that way. We're going in the direction of negative 1i plus 1j, which is different than negative 2i plus 3j. This one is not straight northwest. It's northwest-ish, but it's not straight northwest. This one is straight northwest. And so let's find out. So we'll do a directional derivative, and we'll find out. The directional derivative at the point 1, 1, again, is that partial derivative at the point 1, 1 times u1 plus the partial derivative times u2 all at the point 1, 1. We've already got that work up here. The partial derivative with respect to x at the point 1, 1 is negative 2. u1 would be the negative 1 over the square root of 2. Let me get rid of my compass over here. Plus, partial derivative with respect to y at the point 1, 1 was 3. u2 is 1 over the square root of 2. So this all boils down to, let's see, positive 2 over the square root of 2 plus 3 over the square root of 2 is 5 over the square root of 2. Hope you tracked my arithmetic there. According to my work, you can check my computations here, but I get 3.54. So if you go in the direction of straight northwest, your rate of ascent will first of all be ascending. You know how I know? Positive. You're going to ascend 3.54 meters for every meter that you walk relative to the horizontal. Now the square root of 13, now I'm curious. That ought to be more than that. What's the square root of 13?
The square root of 13 is approximately 3.60555.
There you go. And it's greater than that because we know that this is the greatest ascent. This is not quite. I mean, they were close to the same direction, northwest-ish, but not straight northwest. You would have to go a little bit off straight northwest to get the greatest ascent. Straight northwest is this ascent. Now, what if you maintain your altitude, what directions can you go? Now, I love this question. We're at the point 1, 1. Notice how I label my axes always, always, always. If I don't, yell at me. Now, I'm just going to pretend we have some kind of a contour here just to try to make my point. So if you're at the point 1, 1, and you want to maintain your altitude, that is, you want to stay on that level. See, if you go off that level, you're not going to maintain your altitude. So you're going to maintain. So you should go that way, or you should go that way. At least for that initial step, you should maintain your altitude. So you should go that way or that way. Now, what's the relationship between that way or that way and the gradient vector? Now remember, the gradient vector is perpendicular to the level. So right angle, right angle. So what we would want to do is go in such a direction so that we're perpendicular to the gradient vector. Now that gradient vector, recall, was negative 2i plus 3j. Now, if I want to go in such a way that I'm perpendicular to that, perpendicular to gradient, see if you recall this. The dot product between two vectors, let me just make them up. Vector A and vector B. The dot product between those two vectors was found by taking the magnitude of the one, magnitude of the other, times the cosine of the angle in between. Well, if the angle in between is 90 degrees, the cosine of 90 is 0. So this whole thing gets wiped out to 0. If the dot product is 0, you got yourself some perpendicular vectors. So if I want to make sure that I'm perpendicular to my gradient, thus staying on the level curve, I would want the dot product to be 0. Now, dot product, remember, is this thing where we take this times this, plus this times this, and you want it to be 0. So here's a quick way to do it. Ready? Negative 2 times 3 is 6. 3 times 2 is 6. See, if you just flip them, when you do the multiplication, you're going to get 0. Now, you may have to do some sign, S-I-G-N, like positive, negative sign stuff. But in this case, because we already had a negative there was no need. Negative 2 times 3 is 6. 3 times 2 is 6. So the dot product is 0. So if my gradient vector was that, I should go in a direction that's perpendicular to that. I should go in that direction, or exactly the opposite. See, if one vector is 3i plus 2j, the opposite of that would be negative 3i minus 2j. Either one of those things would keep you on the level. So if anybody says, keep it on the level, man, just keep it level, well, then just ask for the gradient vector and then move in a direction such that the dot product with that vector is 0, and you'll be keeping it on the level.